So in this video, let's try putting together what we know about the tree in order to figure out how much work it takes to explore that search space of sorting a particular input. So here, right, basically our goal is going to be, we want to characterize H, right? So H somehow represents the longest path in the tree. That's basically our worst case, right? So if I want to know what is the worst case, like how much work I have to do to sort something, well, it's going to be based on H. So if I have so H somehow, right, is basically it's my most problematic case, it's my worst case, it's what I want to analyze, right? I want to know what is the most amount of work I would ever have to do in order to solve any possible output that's out there, right? Because H is this height of this tree, and this tree has every possible way things could be ordered. So if I look for H, that's basically going to tell me the most work I would ever have to do. So hopefully what I can do is characterize H and understand what it looks like. So what is the height of the tree? All right, so we'll put together a couple of facts here. First of all, we know that we have to have n factorial number of leaves. Okay, so the number of leaves is greater than or equal to n factorial, right? So we said that the sorting algorithm should be able to sort any input we get. There's n factorial number of possible input permutations, so that means that there's n factorial number of leaves. Okay, so we know this first fact, right? The number of leaves is at least n factorial. All right. Now, second thing we know is that our tree, right, is structured as a binary tree, right? Our decision tree is a binary tree because we have these kind of yes/no questions, is something less, yes or no, right? Is that it's a true or false thing, right? It's a binary decision. So we have this binary tree that holds all of those decisions. Now, it's a binary tree. So if I have a binary tree, right, there's another formula that basically says the following. For a tree of height h, well, for a binary tree of height h, the number of leaves, so a number of leaves is going to be less than 2 to the h, right? So there's this relationship here, right? So the height of my tree, right, is effectively limiting how many leaves I can have, right? Obviously, if I have a tree that's short, I can't have that many leaves. If I have a taller tree, then I get more leaves, okay? And the relationship is this here, right? So basically, my number of leaves is going to be less than or equal to 2 to the h, right? So that's basically saying that you can picture your tree, right? It's like you're doubling. You know, what is the most you can get at the very bottom, right? The number of leaves that are exposed. All right. So, or actually, I should read here. Like the height of a tree of a height h, I can have no more than 2 to the h number of leaves. Okay, maybe that's a nice way to say it. All right. So, what do we do here? Well, somehow, right, we have this idea of number of leaves occurred twice. So I know how many leaves are required to be able to sort any possible input. I also know what the height of the tree is based on the number of leaves it must contain. So, right, so this is a linkage here, right? We're linking that n factorial number of leaves somehow to h value, right? The height of the tree or the worst case. So combine them, we get this expression over here. N factorial less than number of leaves less than 2 to the h. Obviously, you can drop out the middle here. N factorial is less than or equal to 2 to the h. H here is the size of our tree. Probably it's what we want to solve for, right? We want to find out what that most difficult case is, right? How many operations will it take to explore that entire tree? So let's try solving for h. So I have n factorial less than or equal to 2 to the h. I'll take the log of both sides. Okay, so I get this over here, log of n factorial less than or equal to h. And then here what I'm going to do is I'm going to use Stirling's approximation. So Stirling's approximation says the following. Log of n factorial is approximately n log n. Okay, approximately. Do a substitution in there. And I get this over here, right? So this is my final algebra there, right? So n log n less than or equal to h. So basically what we're saying, right, is the height of the tree, right, is at least n log n, right? So in order to reach every single possible input, right? Every input should have a solution, right? So in order to touch every single possible one, right? So touch the deepest leaf from the root, if you think about the tree, right? We need at least n log n number of comparisons, right? So at least, right? That least, what that turns into is a lower bound, right? So that's actually my lower bound for sorting right there, right? So in order to explore, h number of leaves, which corresponds to having the ability to look at every single possible answer that exists based on all different possible permutations of the input, I need to have at least that n log n number of comparisons, right? At least, right? Maybe there's more, but at least, right? So that becomes somehow my lower bound over here, right? So my lower bound, this is my omega now, right, is n log n, right? So in order to visit all leaves in the tree, I need to make at least n log n comparisons.